Hello everyone, my name is Jason Gregerson and welcome to this next video in your Calculus 2 video series. Today we're going to continue on in section 9.1. In the last video we talked about what are differential equations and what are solutions to differential equations. And in this video we're going to talk about the properties or characteristics that we can learn about our solutions just based on the differential equations. So let's go ahead and get started. Alright, so our first characteristic or property is a general nth order differential equation will have a family of solutions that contain n parameters. So what do we mean by this? Well, let's take a look at a basic differential equation. For example, dy dx is equal to 2x. Now the idea is that a solution to this differential equation is some function y that satisfies the differential equation. In other words, the derivative of y is equal to 2x. Now because this is a pretty basic differential equation, we can actually find the solution just by integrating the right-hand side. And so the function x squared plus c would represent all the possible solutions to this differential equation. Right? If we took the derivative of x squared plus 1, we would get 2x, and so on and so forth. So what we see here is that we don't have just one solution to this differential equation, but we actually have infinitely many. Any value for c will make this function y a solution to the differential equation. Now, if we're thinking about this graphically, we can say, what do these solution curves look like? Well, if I looked at the case where c was equal to 0, I would have this parabola. If I looked at the case where c was 1, I'd have y equals x squared plus 1, which would be this parabola. And if c was negative 1, I would have this parabola. So I can see that the family of solutions is really this family of parabolas. Now the next question would be, if I have infinitely many solutions, how do I pick out the one solution that might, fit my specific problem? And so that's what we're going to look at next. Next, we need an initial condition is needed to choose a specific solution out of a family of solution. So all of these curves satisfy our differential equation. So what we'll need to pick out a specific one is we'll need another condition. And oftentimes we'll write this as an initial value problem, which will provide the differential equation, but also a condition that might look like y of 0 equals 1. We can say that what this means is that when x equals 0, y equals 1. And if I use these values into my general solution, I could say, well, I have y equals x squared plus c, but y is 1 when x is 0. That means that c must be equal to 1. That tells me that the specific solution that not only satisfies the differential equation, but also satisfies the initial condition is this equation. So that would be the specific solution. Now we can also think of this graphically, saying that, well, if my condition is stating that when x equals 0 and y equals 1, then my curve must pass through the point that is 0, 1. So if I look at that point on my graph, it would be right here. And so I can see that this curve right here really is that x squared plus 1. That is the curve that not only satisfies the differential equation, but also the initial condition. Now, the thing we're going to pick up in the next slide is the graphical interpretation of this differential equation, but we can talk about it a little bit here as well. Since I have a first order differential equation, it says that the derivative of my function is equal to 2x. But the derivative of my function describes the instantaneous slope along that curve. So in this case, I could say that when x equals 0, for instance, that dy dx would equal 2 times 0, or 0, which means that I should have a horizontal tangent line at that point. And I'm thinking about this parabola, and sure enough, that's what I have. It goes flat here right at the bottom of that parabola. What happens if x is a number that's greater than 0? Well, if I plug a number greater than 0 into the right-hand side of that differential equation, I would get a positive number. So that tells me that just by looking at this differential equation, it tells me that when x is greater than 0, I'm expecting my curve to be increasing, because I expect my derivative of my unknown function to be positive. All right, let's continue on that in the next slide. All right, so a first order differential equation has the form dy dx equals some function of x and y. And the solution to the differential equation is some family of curves, y equals y of x. So we have a family of curves over here. So once again, let's look at a specific example. This time I'm going to look at dy dx is equal to x over y. And so I might go over here and try to sketch maybe what a solution might look like, and maybe I just kind of draw a little sketch like this. And the question is, could that curve really satisfy this differential equation? And without actually being able to solve the differential equation, say that y equals this function, I can still answer the question of whether this curve seems to satisfy the differential equation, because a first-order differential equation is telling me lots of information about the slope of my solution curve. So for instance, if I went over to some point on my curve, right here for instance, I'm going to call that the point 4, 3. I'm just kind of picking out some values here. But that's a positive value for x and a positive value for y. So if I knew what my function was, and I want to find the slope at the point 4, 3, what I'd have to do is I'd have to find dy dx and then evaluate that at that point. But I already have dy dx. It's x over y. So if I evaluate x over y at the point 4, 3, I would get a positive number. I would get the number 4/3. And so the slope at this point of my solution curve should be 4/3. And so that's what I can do. I can evaluate the right-hand side of my differential equation at different points to find out what the slope should be at that point. And then I can make some general statements. For instance, if x is positive and y is positive, then my dy dx should also be positive. That tells me that my solution curve should be increasing anytime I'm in the first quadrant. So as I've drawn out this quick curve here, I see that right here, I am in the first quadrant, but my curve is not increasing. Therefore, this curve could not satisfy that differential equation. It would have to look something more like this, for instance. Now, there's other things I can also learn just by looking at my differential equation. So for instance, this tells me about the slope at different points along my curve, but I could also calculate the second derivative of y with respect to x, and that would tell me about the concavity about my solution curve. And since I have the first derivative, I could simply take the derivative of this piece, the derivative of x times y to the -1, to get an expression for the second derivative. Now, I'm taking the derivative with respect to x here, and I have to do this implicitly because y is a function of x. So I would do that by using the product rule. The derivative of the first thing is 1 times the second thing, plus the first thing times the derivative of the second thing. And that's what I would get here. And now I could clean that up a little bit. I have 1 over y here. I have minus x over y squared here. And putting these things together over a common denominator and then subtracting them, I would get y minus x over y squared. And so I can look at this expression, and this expression will tell me about the concavity of solution curves at different areas in my graph. So for instance, because the denominator is always positive because it's being squared, I could look at the numerator to determine whether it's positive or negative. It looks like in this case, if y is greater than x, then my concavity should be concave up because my second derivative would be positive. And so these are all ways I can explore what my solution curve should look like, even though I don't know what a specific curve is. Alright, so that concludes this video on the properties of differential equations. Next, we're going to look at some applications. Alright, that concludes this video. Thanks for your time.